Morning, colleagues. You're welcome to day 5. I'm thinking that we give participants 5 minutes to join in so that we start with a bigger number and we don't leave others behind, because if we start now, then others will be saying, I'm lost, something like that. So 5 minutes. Let's wait for 5 minutes.
As we are waiting for the 5 minutes, maybe we can get a feedback from some of the participants, how they feel during this training. So you can always write in the chat section and tell us how, what has been your experience so far. So good, as we wait for others. Thank you.
Okay. Thank you very much, Dr. Nyararo. Participants, you can put in the chat how you feel about the last 4 days. Are your expectations being met? What problems do you have? So you can post in the chat. I can see, very good. We are learning so far, very good. So impacting, very good. That is good also on our side. The training has been helpful. Very good, Prof. You feel impactful, we've learned a lot. Okay, excellent, skilling. Very nice, very good skills, I'm learning. Never thought that training would be like this, but he has learned just what I needed, on point. Wow, those are really very good comments. We believe that this training is going to impact on each and everybody, even us, the trainers. We're also getting more experience in R and using R for data analysis, and we are also so excited, and every day is a new day for us. Yes, thank you. R is very hard, but now you get it. Training came at a point when you needed it. You're grateful, thank you. Nice and beautiful lecturers, thank you. There is a poll that has come up, so you can put in your answers. Participants, as we wait for the 3 minutes to end, there is a poll. How has the training, how has been the training so far? So single choice, you can use the poll. You click in the poll and we will get that host and panelists cannot vote. Oh, I thought even me I could vote, but it is okay. Okay. Participants, please vote. How has the training been? You can vote in the poll. I believe you've gotten this window opening on your screen. So just tick whatever you feel like. And we are also going to have an evaluation for today. The 3 questions, we will pop them up before the today's session ends so that you can give us some comments in the chat. And then tomorrow, Saturday, we are going to have an overall evaluation, short questionnaire for you to fill in so that we can improve other trainings. Okay. Thank you. He's touched with the generosity of the trainers. Oh, this one is still struggling, the network. If your network is slow, you can always download the recorded video at the end of the session and listen to the video after the training and catch up so that the next day you are the same level with others. I didn't pick that one. Somebody is proposing that you get attendance certificates. I'll leave that to the forum staff to comment on the attendance certificates. How will the students be evaluated? I'll leave that to Dr. Helen to tell us how the students will be evaluated. Will the videos be shared? Yes, they've been shared. Somebody has missed the link. If you go to the Google Drive, there's a Google Drive which has been formulated. You can get all the recordings. And the poll is showing that so far the training is very good with a percentage of 46%, and others have said the training is excellent with 44%. Very few have said good, and that is really good. Thank you so much for the poll. Excellent and very good. The training has been very good, and those who said good are 9%. And we thank you so much for the poll. Thank you so much for the poll. We've captured the results. If possible, kindly share the Google Drive. Helen, can you share the Google Drive in the chat so that it can be picked by participants? I think we've gone beyond 5 minutes. Can we start? I think we can start, isn't it, Helen?
Yeah.
Okay.
Yes, we can start.
Thank you. Thank you so much. Okay, ladies and gentlemen, we are going to start from where we ended yesterday, and I'm going to share the same screen where we were yesterday. So I'm going to share my R screen, and it's what I want you to go to. So you go to your R and open the screen of R, and also open, because you can see here I have so many things on it, but I have what we call EXPA Lab 1, Experimental Lab 1. So that is where we are going to use EXPA Lab 1. It is the R script that we are going to use. So everybody should open their script, and remember that when you want to use R, the first thing we do is to load the packages that we are going to use. And after loading the packages, we browse and get our working directorate, so that when we want to download a file, then we can access it quickly. Okay? So that's what we are going to do now. Remember, yesterday we talked about generating a field sheet where you can enter your data, and in that field sheet, you've already got randomized treatments to the experimental units. So you can now write it as a CVS file and open it in Excel, and then print it out and go to the field. Now, we only looked at complete randomized design and randomized block design because of time, but I want to encourage you to go in Google and put in Agricola. If you just write Agricola in Google, you will see a gentleman called Felipe. How do you load Xlab1? It's a question in the chat. You can either go to File, Open, then when you click Open, it takes you where your files are and look for Xlab. You can see mine is there, and then click on it and it goes in and you click Open. So File, Open File, then it takes you to the documents, browse the folder where you're saving your R files, and then look for Xlab1. So I'll not open it because it's already opened. So hopefully those who don't have Lab1 already have it. XP means experimental lab, laboratory 1, meaning practical. We are doing a practical session. So as I said, let us load the packages. I am going to load whatever is here. It takes only a few minutes. So click load, then they will load all of them at once. Don't mind about the reds. If you want to mind about them, then you read the details, but they do not have any problem. So long as you see blue, it says you see library in blue, all of them are loaded. If they are not loaded, you will see a message saying that library Agricola unsuccessfully unpacked. So once you see there's no message like that, you know that your library packages have been downloaded. I hope you're following. So I am going right where we stopped. So we went through this yesterday, and we are going to mainly use library Agricola and DUE. So yesterday, we finished exploring the ways we can generate field sheets for a complete randomized design and randomized complete block design. And these are the only two we could cover in this session, but there are many. You can generate a Latin square design, designs with factorial treatment structure, incomplete block design. There are very many, you can't even finish them. Even lattice for those doing plant breeding. There are so many. Just go to Google, put in Agricola, and Agricola is a package which helps you design most of those designs and experimental. So don't get stuck that your design has not been mentioned. It's like when a child is born and is 1 year and would like to start walking, they don't immediately walk and then run. So that's how we are. We start slowly, and then you will go to Google. Now we've pushed you, you can stand up. You're going to go on your own and Google. The errors you get, just highlight, put them in Google, and you get an answer. So don't get scared. I continue saying that because I know what I went through. So I don't want you to be like me. I want you to be really excellent learners of R and don't get stuck and scared of R, okay? Okay, we go on. So the first thing we do after we've loaded our packages, we get our directorate. So as usual, you can use the menu bar by clicking Session, then Set Working Directorate. After that, choose the directorate. So that's where I am. Session is on the menu bar of RStudio. Then click Set Working Directorate. Choose Working Directorate. So you click Choose Working Directorate and then browse to where you have saved your work. I have saved mine in R package. So this is the name. I click and specifically a particular folder called Slides. So I open. So once you do that, you will see a message in the console saying set working directorate and the path to that directorate. Are we together? Is that okay? So if you've not done that, then we'll not be able to proceed. So let me just see in the chat what people are saying. If it's okay, we continue. And I can see that Xlab has been posted in the chat. There are some people saying no, please. So if you're saying no, please go to session, set working directorate, choose directorate, then browse to the folder where you're keeping R files and dataset, because that's where forest is, where you stored the file called forest. Okay. Okay, since you people are saying yes, I hope even those who had said that no are at the same pace with us. So after that, we are going to import our data set, forest. And you see I'm going to highlight the command for import. So you can either write it or you just run what is in the script. So if you run what is in the script, then it becomes so easy for us, because then it's going to pick the data set very, very fast. So run that line, forest assign to read.scv, and the file is called forest.csv. So we are going to run that. And if you want to see what you've run, you can actually type forest and run, and you will see in the console that the data has been printed. It consists of species and growth. So yesterday we looked at how to design the field sheet for collecting data and experimental design. Now we assume we've collected the data, and the data is called forest, and we are going to look at summaries. How do we summarize our data? That is the next thing we are going to do. So species has A, B, C, D, so we have to convert it to a factor. So the next line we are going to run is species assigned to a factor. So the first word species is the name of the object. In R, we could call them files. The file where this command is assigned to is called species. So the object in R called species, we assign a command that you change it to a factor. And the factor that we want to change is called species, and it is found in a data set called forest. So this part here in the bracket, we have a data set forest, and within that data set, look for species. So let's run that. The next line checks whether the variable species is really a factor. So you can write class in bracket species. Remember, R is case sensitive, so if you write lowercase species, then you may get red marks. So you just have to go and change the variable species the way it is written in your file of forestry. Now let's summarize. So summary in bracket dataset, look for growth, because growth is the continuous variable. Now we need to get summaries. We click that, and you see in the console down here, they are summaries. We have the mean, the first quartile, the median, the third quartile, mean, and maximum. Okay, so these summary statistics, you are conversant with them. The only thing we can really mention now is that median and mean are measures of central tendency, and median is used mostly when the data set is highly skewed. For example, income. If we are going to do a survey of income of people, might find some are earning really high and others earning really, really small. So if you use the mean as a measure of average income, you might get a wrong impression, because what is going to happen is that the high value is going to pull the mean towards it. So the average income will appear to be high, and then people will think they are doing well, yet they are not doing well. So median is the best way to summarize income, because median is not affected by outliers. Okay, outliers are values which are extremely low or extremely high. So that is to mention in passing. Then we have to use this library called dplyr. So make sure you've run dplyr. It's going to help us use the pipe. Yesterday I told you these percentages greater than percentages is called a pipe operation in R. It's like where you want to pass through your command. You don't want to write line by line, and keep adding and subtracting. So you just want to write them at a go and then run them. So you make sure dplyr is loaded. So you can just run dplyr, and once you don't get any problem saying not loaded, then you know it exists in your R software. Now, under dplyr, we want to use summarizing growth by species, because we had 4 species and we are looking at summary statistics. We've already got the overall growth. Now we want to see by species which one has the highest growth. So we run this. So you can see this is one line, but has been broken into 3, but they are all connected by this operator called the pipe. So let's run that. And you see that it's giving us the means. When we look at our consoler, we will see the means. You can copy them and take them to our document, make them beautiful, and then put the units and define the species with their botanical names. Now you're writing your project or your paper to publish. You won't publish species A, B, C, D. No one knows that in the world there's a species called A. So you have to write the scientific name of A, B, C, and D. And then you write growth with its units of measurement. That's how we present our data for publication. So once you've transferred your data to a Word document, then what you also have to do is to write around it. Don't wait for the supervisor to write for you. You have to interpret the information. So we are interested in knowing which species has the highest growth rate, which is species B, given that it has an average growth rate of 37.4, and the one with the lowest growth rate is species C, which has 19.5. So from those results, we know that we've seen that there are differences in magnitude. We can now, after doing our descriptive statistics, go and do inferential statistics, which is going to confirm the differences we are observing now. And yesterday when I asked that question, I got very beautiful answers. You told me that we can use an analysis of variance, one-way analysis of variance, to test for these differences, which was really excellent response. Okay, so this is also a reminder that if you have one factor and the groups of that factors are more than 2, then that qualifies for an analysis of variance, one-way analysis of variance. If there were only 2, we would use a t-test. And if those 2 are independent, we use a 2 independent t-test. If those 2 are paired, like we saw in our example, whereby one plant, we are measuring the seeds at the bottom and the seeds at the top. Those information are correlated, even if there are 2 groups, but because they depend on each other, they are on one plant, we use a paired t-test. So those are 2 different things. A 2 independent t-test is used when the values you've obtained do not affect the value of B. For example, the growth of A is independent of the growth of B. So in the other example we saw where we had plant part, bottom and top on the same plant is feeding the top and the same plant is feeding on the bottom. So the growth of bottom part has an impact on the top and vice versa. So there is dependence, there is correlation. So in that case, we used a paired t-test. Okay. Now there's a question here. Explain these little squiggles here. I have highlighted them in blue. It is called a pipe operator in R. Just like you know a pipe, it is hollow. So you pass through the one command without using plus or minus. You will see that in other commands we are going to use plus, then you use addition. Or on the other hand, if we had to write group, we have to write it as an individual command, then summarize as an individual command. We also have on each of these, as we say group by, we have to specify the data. But you can see that we've specified our data at the beginning, forest, and it is working for the group line and also working for the summary part. So this way of writing our R command just helps us to write fewer sentences when running R. So how do we keep the three lines connected? You can see that it is the pipe operator which is connecting them. We put a pipe at forest and at the by command. The first pipe connects to the second, and the second line is connected by this pipe to the third. Any other question? Let me check the chat. Please resend the links of the drives. Helen, you can do that. Okay, let's continue. So if that part is fine, can I see some comments in the chat before we go to the box plot? Okay. More comments? I want more comments. I'm waiting for comments for that section. Okay. Okay. Somebody has said that Q&A is the best place for posting the documents. Helen, post the documents in the Q&A. You post all the links. Okay, so it is okay so far. So the next thing we are going to do, when you are doing exploring data, you do not end with the summary statistics, only the numerical summaries. We also do the graphical summaries. Graphical summaries help you to know the trend within the data. It is the easiest way to explain to somebody who has not done statistics what your data is about. For example, if you go to your grandmother in the village, with these summary statistics down here, the means is she will just look at you like, what are you talking about? Is that money or something? But if you go with a figure, then she will understand that there's something you want to communicate. So the box plot the graphical summaries simplify what you want to communicate to the community. And also, when you are writing your project, if in section A you've drawn a table, then in section B don't draw a table, you draw a graph. And if information in section A where I've presented a table is the same information you want to put in B, section B, then refer to table 1. Don't draw a graph for the same information because it will be the same thing you're talking about. So if it's the same thing you want to present, then you refer table 1, see table 1, or in bracket table 1. Now you're talking about the highest growth rate of species B is 37.0 grams per hectare. In bracket table 1. This species is similar to a species found in West Africa. And this was done by Nana et al. I'm trying to show you that now you're writing your data, your results section, and you're also discussing as well. Okay? Let's now construct a box plot as one of the methods we can use. Yesterday we talked about a box plot, and I just wanted us to do a recap. And this is the line we use for constructing a box plot. And I'm going to run it. And there we are, we have our box plot. This is where we ended actually. And I'm going to zoom in. Before I go there, if you look where you see those little boxes, you will see export. And if you click at that down arrow, you will see it says save as image, save as PDF, copy to clipboard. So you choose whatever you want. But I think it's better you copy to clipboard, then you take it to a Word document and start writing around. Okay, so I'm going to zoom in. And we talked about this yesterday. We say the black line shows the median. The box plot is a 5-point summary. It consists of the minimum. Then the first boundary of the box plot is the first quartile. The black line is the median. The median represents the value which occupies the middle position when the data has been arranged in ascending order. Then the last part of the box plot, the boundary, is the third quartile. Then we have the maximum. When we looked at these box plots, we saw that there are differences because you can see species A has species B has the highest median, followed by species D. So now my grandmother would easily understand this now, because now I tell her that you look at this black line, that is the median. What does the median show? It is just an average. When you add 5 divided by 5, we get 1, that is the median. And they will easily understand compared to the numbers. So that's what graphical displays represent. And we are able to compare the distribution between these groups. We can look at the variability. We talked about it yesterday, the spread. We talked about if this line, the black line, was dividing the whole of this box plot in 2, then that would be normal distribution. Anything different from that is skewness. And I said this top part is the right and the down one is the left. So if this bigger part is on to the left, just like you see in A, to the right, just like you see in A, we say that the data is skewed to the right. And in species B, the data is skewed also to the right. In species C, it is skewed to the left. And this also applies to D. Okay. Any question before we go to the second last thing? Okay, there's a question that why should I calculate the mean and the box plot is showing us the median? I zoom it out again. Let me look at this, how we're calculating. If you look at the box plot command, we are not computing the mean anymore. We just told the R that we want to construct a box plot. And from statistics, a box plot is a 5-point summary, as I've mentioned. The first part was to show you how to compute the summary statistics, the mean by species. So we finished that part of numerical summary, and now we are looking at the graphical summaries. And the first one we've drawn is the box plot. Okay. So this is the box plot, and the middle part is the median, not the mean. Okay. How do you interpret B? Explain the variation in sizes of the boxes. Okay. So if we want actually to look at the magnitude of the variation, we can compute either the variance or standard deviation. Now, looking at these box plots, we can see that the one which has a wider box plot is more variable compared to those with smaller box plot. Because if we flip this box plot and they are lying on this side where my cursor is, and draw a line around it, we'll see that this one has a fat curve compared to this one. This one has a bigger curve. So these two are less variable compared to A and C. Because of the spread from the median, the values are far away from the median, meaning that there's more variance in C and A compared to B and D. They are not seeing, okay. Are you seeing this? Let me share this one. Maybe you're not seeing it. Okay. Sorry, I thought they were. Now, can you see? Can you see the zoomed? I thought it was automatic, but I'm told that you can. Okay, so sorry about that. I'm saying that when we look at these box plots, as I mentioned, the middle part represents the median. And you remember that median is a measure of average, a measure of central tendency. And we know that variability is the average square difference between the observed value and the mean. And if the median is representing the mean, if values are far away from the median, that means that there is more variability within that group as compared to group B. Okay, so if we look at group A and B, group B has less variability given that these values are more closer to A, to the line as compared to these ones. So that's how variability is explained. So if the graph is more peaked, then the values are more closer to the mean than when the graph is flat. Okay. Can we include, no, the box plot is only made up of the median. I have not seen a box plot constructed by the mean, but we can construct bar chart using either the mean or the median or the mode. The only box plot which has median, mode, and mean being the same value is a normally distributed box plot. Wherever there is normal distribution, we will find that the mean, the median, and the mode are the same. They have the same value. Okay, that's where we'll find a box plot with mean, median being the same, and one of them can represent the middle line. Okay, so I'm going to stop sharing this and then share the other screen so that we can finish. Today, we want also to introduce something of interest called regression. So I want us to move a bit faster here and finish. So we want to construct a histogram. The next bit is to construct a histogram. Control plus, okay. Okay. Is that more clearer, the fonts? Okay, so we are going to construct a histogram. What is the use of a histogram? Can I see some responses in the chat? What do we use a histogram for? Why do we construct a histogram? Let me check the chat. Why do we construct a histogram? Explain normal distribution. Yes, it is clearer. I want to see why do we construct a histogram? testing the distribution, showing the distribution of the data for comparison, high and low frequency distribution, shows the frequency. I'm reading your responses, shows the mode, to check for skewness. Okay, continue the responses. Okay, great. See normality. Summarize, continue, visualize the normality of data. Great, excellent. That is really good. I'm happy. Thank you so much. I'm going to close the chat and then come to the R window. So a histogram is used to display the distribution of the data. The distribution can be normal distribution, it can be Y-bar distribution, T-distribution, it could have a chi-square distribution, etc. But the histogram helps us to know the distribution of the data. So we are going to construct a histogram, and a histogram in R requires that we know the number of values, the mean, and the standard deviation. So we come here. B is just a name of an object. Summarize is a function asking you to summarize the file forest and look for growth. That's where we want to summarize our data. We've already done this, so let's see. Run. Saying that. Okay. I have a red. I am going to reduce this screen a bit. Okay. Let me first of all clear this red. And okay, so let me run this again and see whether it will bring the same problem. Now it works. So you see this red thing here. It is not really, don't get scared when you see the red. You see, it was about the sizes of the windows, not anything to do with your command. You see, R just needs you to be patient, and you also show that you know it, so it doesn't, trouble you anymore. Okay, let's continue. So I have produced the summary, which has the mean of growth, the first quartile, median, mean, third quartile, and maximum. And I want also to know the standard deviation. There we go. So if you want to know the standard deviation, write SD for standard deviation, in bracket the data set, which is forest, $growth, meaning that in forest, look for growth. And I want you to calculate the standard deviation of growth. Now we are going to construct the histogram, and we are calling this line here, which we are telling R to construct the histogram, growth. So growth is equal to, or assign a normal distribution. N is equal to 24, mean is equal to 12.25, and SD is 7.07. Now, these are values that were default in the computer, but you can use the real values in your data set if you prefer. So then I will run that and run the histogram. So there we are. Okay, so this is our histogram. You can see growth on the x-axis, the frequency on the y-axis. When you are constructing a histogram, we need frequency, so you have to group your data and then get the frequency. But in this frequency, I'm also getting negatives. So probably there's something wrong with my data. This is one way of finding out whether there is a mistake. So you can say I have -5. So I need to find out, is there a negative growth? And it has a frequency of 1. So there should be a mistake. We shouldn't have negative growth. But a histogram is supposed to show us, let me share this so that it is visible. I don't know. Okay, so the histogram, I hope you can see the histogram. So who can tell me the distribution of the data? Can I see some answers in the chat? What is the distribution of the data? Somebody is saying skewed, normal, skewed to the right, symmetrical, skewed to the left, normal distribution. Wow, that is interesting. Negatively skewed, positively skewed. Okay. Okay, let's close the chat. So if we look at this distribution, where is the longer tail? Is it on the left? This is the left. You can see my cursor. This is the left and this is the right. So where is the longer tail? Is there a tail which is longer? There's no tail which is longer. On this side we have 2 boxes and this side we have 2 boxes. So if that is the case, if we draw a line along in the middle of this graph, we shall see that this side is almost equal to this side. So we cannot say this data is really skewed. It's almost normal, isn't it? What do you think? Let me see your expressions in the chat. It says left skew. Because the skewness, we should have more, the tail should be longer on one side, either on the left or on the right. But we can see that our tails are both the same size. So it is normally distributed. Somebody says normality test. Yes, we can do a normality test and it would confirm whether the data is truly normally distributed or not. Or we can look at the value of the mean and the median when we go back to the output. Yes. Okay, so I'm going to stop sharing. I'll go back to the screen and then share our screen. Okay. So we've seen how to construct a histogram. Then I also put, I was just trying to put as many functions as possible that you can really investigate with your data and see whether you're interested. So you can summarize using the dplyr function. We can also summarize our data. I think this one you can do in your free time, the dplyr. So what we are going to do is to go to something else that we haven't seen. So the graphics of function clears the graphical plots. You just write graphics.off, close brackets. Then when you run, it will clear the plots so that we can have something else. So I also wanted to show you that we can use the ggplot to construct a box plot. And I had people talking about, can we use colors instead of palette? I have both of them here, and I'm just going to run these 2 for that purpose. So when we run the first one, which says ggbox plot, forest is the data set, X is the x-axis, the horizontal axis, Y is the vertical axis called growth, and then color equals species. Then the palette, these palettes, you get them from the R language. Then I said, no, I don't want to write this 00AF. I'm going to put the colors. So I wrote the same command up here, below here, and instead of 00 hash, I put palette, put together gray, blue, red, black, just like you wanted. So let's see what happens. So we run that. We get our box plot. You can see it. Let me zoom it with those colors. Ooh, I stopped sharing. There we go. If you click graphics off, you've cleaned the plot section. I'm assuming that you have already exported your graphs to another document. You won't find them again. So you only do it when you want to clear that window for other graphics. So you can see the box plot as we had them before with these colors. The main aim here is to show you that you can use the palette, or you can actually put in the color to draw the box plot. And you can vary the colors for publications, unless if you are allowed and you're ready to pay for colored printing, you can produce your graphs in color. Otherwise, you can vary the gray color or the black color and draw your box plate in a gray, which is acceptable black. So we've already talked about the interpretation. I just want to show you that we can play around with the commands and draw different things. So let's have the last one. Same command, but instead of the palette having #00AF, I put colors. So I'm going to run also. And there we go. Let me zoom this. And you see that now it is another share. I didn't cancel the previous one. Okay. What do I do? Okay. I didn't cancel the no, it is the new one I'm sharing. Okay. I thought I hadn't canceled the previous one. But in the colors, I have gray, blue, red, and black. So let me share this so that you can see it visibly. Okay, I hope you can see. So the main aim of this is, some people are asking, can we put the names of the colors instead of those numbers of the palette? Yes, it is true. You can put the names of colors and draw the same box plot. And remember, when you construct a figure, the title of the figure goes below the figure, not on the top of the figure. Okay? So let me stop sharing this and we do the last bit so that I can leave you to get knowledge about regression. So the last thing I wanted us to see that I know that you're interested in so much is the error bar. I believe everybody wants to draw bar graphs with error bar. So what I'm going to do is to write graphics of graphics.off, isn't it? There we go. Run. It clears my plot window. I've just written graphics.off that clear the graphics window so that I can produce more graphs. So that this is the last thing, that is the error bar, and we use the ggplot, data equals forest, some word, which I think I didn't go to nursery, so I can't pronounce these words. I'm sorry about that one. So this word here, this thing, AES. I know you're laughing at me, but it is okay. You know, if you look at me very well in this figure, you will see that my hair is turning white and black. So I never went to nursery. Okay, so in this aesthetics, we are trying to say that plot our X and Y on a graph. with all things like the mean, geometric, the geometry, we want them to be bars, and we also want you to put error bars. So what I'm going to do is to run bit by bit. So I'm going to run the first bit and make the others inert so that you see what I'm talking about. This is the last thing, and I want you to pay attention. Okay, the first thing I'm going to run is this. I also want to remove the addition sign. I make it inert so that it doesn't disturb me. So let me run. What does it do? If you look in the lower section, the right bottom corner, you will see a graph drawn, and it is empty. So afterwards, you start running the second part. So I'm removing the comments. I'm running the second bit, and I want it to, so there we are, positive, run the second bit. Pardon? Okay, let me remove this positive here, put a comment, and then run again. I hope you're following. I just divided the command. So when I run that part, it has put in the bars. Remember, I've told it that stats underscore summary is a function that summarizes my data with the mean, and you're going to use the geometry, the bars. But on the bars, I want you to put error bars, okay? I want you to put error bars. So I am also going to make the last part inactive so that it puts my error bars. Okay, there we are. And let's see. There we are. So we put this. So there we go. Magic happens. There's no magic here. I'm just joking. Oh, okay, let me. Okay, let me first zoom it out. Okay, let me first copy the thing and paste it in the chat. I'm sorry. I discovered it last night as I was going to go to sleep. Copy, and I didn't update. Let me paste it in the chat. Okay, I am pasting the commands in the chat. There we go. So receive them and put it in your script. But as well, I'm going to zoom this and explain it. Then I give you minutes to do it, okay? So please pay attention. We explain this part of the error bars, and then I can leave you to practice. So error bars, how do we construct error bars? We've used the mean, but once you tell R that you want error bars, it is going to pick the standard deviation in your data and use it to construct this black, you can see the black line. It is like a confidence interval. And it's placed in the middle of the box. In between here, we have the mean and the standard deviation, the way you calculate the confidence intervals. So the R has calculated the confidence interval for A, for B, for C, and D, and located them on each bar. Why do we do this? We want to find out, is the average growth for A significantly different from the average growth of B? How do we find out? If these lines, you can see this line, I hope you can see my cursor. This symbol here, is it a symbol or a line? A symbol. Let's say it's a symbol. It's like, huh? Did I zoom? Okay, sorry about that. Sorry, I thought I had zoomed. I'm sorry. Okay, can you now see the chart I'm talking about? Thank you. I'm sorry about that. Okay, so I'm saying that why do I draw error bars? The first thing is that we draw error bars for data which is independent from the other, meaning the growth of A is not affected by growth of B. That's when we construct error bars. Okay? We also construct error bars to find out whether there are differences in the treatments. And they are constructed after you've run an analysis of variance, but here I was just showing you that this is the way you construct the error bar. So when you run an analysis of variance and you find that overall there are significant differences, then we want to find out what treatment is contributing to the differences. So once we see them, we want to find out, is A different from B? We use the error bars. Now, if the error bars are not overlapping, let's pay attention on A and B, the pink one and the green one. You can see that the error bar of A does not overlap with B, meaning that the difference between A and B is statistically significant, or the average growth of A is statistically different from the average growth of B, because these error bars are not overlapping. You know, when things are overlapping, it means that the values in A are the same as the values in B. Now, let's go to C. You look at C. If we look at C, I'm going to move my cursor from A and move to C. Can you see that the values in A are also found in C? That means these two are overlapping. And because they are overlapping, it implies that the mean values of A also could be found in C. So meaning that there is no significant difference between the growth of A and B. Those are not different. But A and C, sorry. Let me repeat myself. There is no significant difference between the mean growth of A and C. There is significant difference between the mean growth of A and B because the error bars are not overlapping. When we look at B and C, the error bars are not overlapping, meaning there is no significant difference between the growth of B, meaning there is significant difference between the growth of B and C. When we look at C and D, they are not overlapping, meaning C and D are significantly different. The growth is significantly different. That's what I wanted to give you, so that in case you find that it is suitable for your data, you can always use it. Any question? Let me go to the chat. Oh, somebody says I didn't paste the chat. Let me paste them again. Okay. There we go. I've pasted the commands in the chat. Please share the modified script. Yes, I'll do that after the session. Please repeat, okay? What of B and D? They seem overlapping. Let me see. Paste in Q&A. Okay, I'll do that. Paste in Q&A. I'm going to paste in Q&A and send to all. Okay. I have done pasting in Q. I can't see the paste. Yes, because it moves very fast. There you go. Okay. Now I understand. Thank you. Okay. You're welcome. Okay. So somebody said that why don't we start with construct error bars? That question is to the people who made R, but we will also think about it. You know, R is so flexible. You can also come up with your commands and publish them. So we'll think about writing construct box plot instead of starting with what is written. Then the other one said I should repeat the interpretation. And I said that I'm going to use, somebody said, how about D and B? Do they overlap? Yes. D and B overlap. You can see this is the error bar for D. It goes and overlaps with B. So meaning that B and D are not significantly different. But B is significantly different from A and from C. However, A and C are not significantly different. Their growth rate is almost similar. Okay. Okay, so let me see if there are questions. Any questions? How do we arrange bars by height, starting with the tallest? How do we arrange bars, starting with the tallest? How about A and D? I've talked about B and D. Let me see. A and D do not overlap. If you draw a line, A ends here, so if you run it across, they do not overlap. But D and B overlap. Okay? So when they do not overlap, then there are significant differences in the mean growth. If they overlap, then there is no significant difference in mean growth of those two treatments. So this is one way of doing what we call pairwise tests, but just using error bars. Okay. Let me check the chat if there's any burning question. How do we get to learn all these commands? One, you need to be patient. Secondly, you have to use Google all the time because R is an old software, but because of its command-based, people normally don't want to use R. But what you do is whenever you get an error, paste in the Google. If you want to construct an error bar graph, just put in Google, how do we construct an error bar using R? Or you can actually use the help command. Let me stop sharing this and we go back to the screen. I'm going to use the next 5 minutes so that I can allow my colleague to come in with regression. So if we go down here in the console and we put in help, so I'm going to type help in the console, help in bracket, error, or I can put bar error, bar.error. You can see it is already there existing, bar error. Then once you enter, you see information in the right bottom corner saying plotting standard error and standard deviation on plotting standard error or standard deviation over multiple comparison of means. So you can now read about it, you see? So you can read about it. So whatever you don't know, You can use the help command, or you can take to Google actually, and Google will help you to get these things, because R is still developing, unlike SAS, which is already developed. You can always get the things, and many people have gotten problems using R, so the answers are already there in Google. When you put in, when you get a red mark coming up in the console, copy it, put it in Google, and you will get these commands. We do not have these commands off head. Nobody can put all these commands in your head. You may not be able you may not be able to put in something else, since you have so many subjects to do. That's why we always open the script. But because of experience, you know that here I need geo equals bar, something like that. But always use the help command, use Google, because here we've shown a very few things. You can always Google, how do I construct bars arranged in ascending order, which is called a Pareto diagram, and it will come up, okay? Something like that. So you can see that I'm saying end in my script, and this ends the part of exploratory data analysis for experimental design. You can see that I didn't construct a frequency table or a percentages, because our data is continuous and we just need to summarize it by groups. So when we have continuous data, we only draw things that require us to summarize the original data. Do not go and formulate groups in your growth data, which is continuous, and then draw bars or a bar graph. If you want to draw a bar graph for continuous data, use mean, so that you don't lose information. If you use frequencies, so what are you going to interpret, you know? So frequencies will suit categorical information. So if we have quality and color, then we can get frequency of color, frequency of quality. So those are the differences. You can see that yesterday, the other day, when my colleague was talking about exploratory data analysis, she used frequencies, she used bar graphs, but you can see that they were frequency-based, not mean-based. So you see the difference. When you have continuous data, use what is suitable. Okay. If there's no question, I would like to say bye. This ends this bit. I'll come in tomorrow. Hopefully my colleague can finish today what she has, but we are not going to rush you. We are going to go step by step. I am going to leave the floor for my colleague, Dr. Helen, to come in with regression. I believe that you're getting excited. It's like you've been eating chicken, then they say, now it is time for beef. You start salivating. I believe you're also salivating for regression. Thank you very much. And I will now leave the floor for Dr. Helen says you're starting with correlation, then after correlation, you go to regression. Thank you very much. Okay, let me see in the chat before I sign off. Okay, thank you very much. Yes, tomorrow, Saturday, according to the program, we shall be here. We shall be here and we will continue. Okay, thank you. Mute. I'm going to
Can you hear me?
Yes, now it's okay.
No, cool. Okay, a very good morning to everyone. Yeah, it's good afternoon, sorry, in Kampala. Welcome back from Professor Susan's session. Now what we are going to do, there are some quick questions that were asked if we can export results from R to Word directly. I don't know if time will allow, but that one can be done using the R Markdown, whereby you can see all your results within the Word document, and you can maybe just copy and paste them. So the point is, give yourself time with R, and then you'll be able to learn as more things as possible. So let's move on. I'm going to share, hope time will be enough for me. I want to discuss correlation coefficient and then a regression analysis. Let's see how the going is going to be. So I'm going to share my screen. I'm still using the diamond data. So if we are the moment to go to R, in all the presentation that I'm going to do, I'm going to still be using the diamond data. Some of you had saved it as the lab_data, so we'll go on to that. So right now, sometimes if you're analyzing data, after the descriptive analysis, you do not stop there. You need to take another step. You move on to bivariate analysis, and after bivariate analysis, you move on to multivariate analysis. But now let's start. As you see the word bivariate analysis, we are going to do. We are moving on now. We are looking at two variables. Bi means two. In the descriptive, we're doing. All what we've been doing was univariate analysis. So under here, we are going to look at the description by groups. I'm going to be a little bit fast because most of the information has been shared by Professor Susan. It's like, I don't want to repeat myself unless when it's necessary. Then a little bit on the correlation coefficient background, which I still guess that some of you have got this particular information. And then we go to R. We are going to see how do we get a correlation in R and then a correlation matrix, only those two things. And then more work can be done when you use Google. So descriptive by groups. Actually, even I saw a question in chat asking when Professor Susan was showing the descriptive by groups, what you have to note at the back of your mind that most of the time we do a descriptive by groups when you've got one continuous variable and one categorical variable. From what Professor Susan has just shared, okay. Let me ask in the chat, can you hear me now? Okay, sorry about that. Yes, I was talking about descriptive by groups. Given that now where we have reached so far since Monday, a lot has been done. So we can try to see that we increase the pace. I was saying that for you to use descriptive by groups, you have to have it at the back of your mind, whereby somebody's saying that I don't have slides for correlation. Okay, then Professor Susan can share that. When you want to do descriptive by groups, one thing you have to put at the back of your mind is that it is done with two variables, one being categorical and the other one being continuous. From what Professor Susan shared previously, we had species, whereby they had 4 categories, and then you also had growth, which was continuous. So when you're grouping by groups, you can ask anything, whether you want to get the mean of a categorical value in response to the continuous one, or you want to get a standard deviation, depending on what you want to do. And then you can command R to give you all that you have. But I have this part in R, those still profiles just explained about it, but I'll go to R and then I'll go through that particular detail. Let's just move on and see. Still, when you're doing descriptive by groups, we produce box plots. And that one has, I guess that you've got a thorough explanation on what has been done. What you have to note at the back of your mind is that you have to know the number of your groupings. And then the number of your groupings will give you the different box plots that you need per label. I'll do that in R, but let's just go through the theory briefly. So within correlation coefficient, which is sometimes denoted as R, most of the time you might ask yourself, what is the relevancy? So we want to investigate the strength of association between two variables. And at the same time, you want to see the direction of that particular relationship. There are two things. What is the strength of the association, and then the direction? When I talk about association, it means what is the value of the correlation coefficient that you have. And then usually the correlation coefficient, which is R, lies between -1 and 1. And then during the analysis, you can go ahead and say whether it was a weak association, or it was moderate, or it was strong, depending on the value. We are looking at -1 and 1. And we use the correlation coefficient if you're looking at numerical values or continuous values. In our Diamond data set, we're using price, length, width, among others. The moment it comes, and when you're looking at what about how do you decide the direction of the relationship? For you to decide the direction of the relationship, in this particular case, what is most important? You have to check the sign. Like I said earlier, the correlation coefficient lies between -1 and 1. So the sign is the one that tells you the direction of the relationship. With a minus sign, for example, in case we take the extremes of -1 and then +1, with a -1, it indicates a strong negative correlation. So in that particular case, as X increases, then Y will be decreasing. 0 means there is no association. And then in case you've got a +1, that implies that is a positive, a strong positive correlation. And in that particular case, Y increases with X. Okay, now let's briefly just take a little look on how pictures would look like. When you look at the pictures on my slide, we see the first one on the extreme left, whereby it has got, we plotted the relationship between variable X and Y. So from the figure, we are seeing a negative relationship that as X increases, as X increases, Y decreases. And when you look up here on the correlation coefficient R, it is saying that it is -0.86. So now it is us to judge, is it strong or not strong? But at least the direction is shown as a negative. When you come to the middle one, what you're seeing that the blue line, that my R is equal to 0, the correlation coefficient is 0. And the way how my data is scattered with the dots, I mean, you cannot quickly tell whether the line really fits the data very well. So in that particular case, there is no correlation between X and Y. And then in the last one, you see that the line of best fit is moving upwards, and we are looking at a relationship between Y and X. With R being positive, we are told that it's equal to 0.87. And then we judge, is it, the moment my R is above 5, do I say that it's moderate or it's strong? When it is less than 5, towards the negative, what comment do I put? Those are the things that we're going to look at. So now, in R, we are going to look at various commands, like call R, which gives you the correlation coefficient, and then the call.test, which returns both the correlation and then the p-values. However, as you move to R, you're supposed to put at the back of your mind that we know that there are 3 types, or there are more than 3 types of correlation coefficient, but the common one used are the Pearson, the Candle, and then the Spearman. So you have to have at the back of your mind, why am I using Pearson? Why am I using Candle? And why am I using the Spearman? Such that by the end of the day, you don't produce wrong result. You know, when it comes to programming, when you input something wrong, yes, you'll get result, but the results will be wrong. Okay. Now, Pearson, which is the common one most of us know, that is used mostly on continuous variables. Like within our data set, we've got different continuous variables. And so we need to check whether there is a statistical relationship between these variables as we move on. Whereas when it comes to Candor and Spearman, most of the time they're ordered in a certain way when you've gotten ordered data, and you have to depict that from the data set. For example, when I mentioned earlier about the different levels of measurements, is it nominal or is it ordinal? So with ordinal variables, there is some order, so you have to look at. And then the other thing, most of the data where we use Candor Spearmans, when you're looking at a Likert scale, because it is also ordinal in nature, whereby it is like a very strong, most of the time when you're looking at maybe testing the satisfaction, less satisfied, and so on, that kind of a Likert type. And in this case, you want to test whether there is a differences between the ranks of the corresponding variables. I was just giving an example of when you can use a Candor and then a Spearman's, but in our R, we are going to do a correlation. We're going to do a Pearson. These are visualization that I want us to do in R, and then I will proceed. This was just an output, and then I will look at the interpretation of results in R. And then the other thing that I want to share with you briefly is about a correlation matrix. You know, when you're doing a correlation coefficient, you can do it with only one variable. However, still, you can run a correlation matrix such that instead of running one variable, you can run as many variables as possible, provided they are continuous, and see how they are correlated to the other and if there is any relationship. So instead of running one by one, we'll be using a correlation matrix. But for us to use a correlation matrix, we are going to use a command rcol, RCORR, then bracket command. And we are going to pick this from the HMISC package. I'm just wondering if you already installed this particular package, but it's what we're going to use in case we want to run a correlation matrix. And in this particular case, the HMISC package will help us to get the correlation coefficients together as well as the p-values. Right now, I'm going to close this and then we move on to R. After running the correlations, then we'll move on to regression. And somebody is asking, what is the difference between Spearman's and then the Candor and then, like I mentioned earlier, that when it comes to Pearson works mostly on continuous variables. When you look at our Diamond data set, when we check the structure of the data, most of the data, we had variables that were numerical in nature, that were continuous. We had weight, we had depth, we had length, we had depth, we had, yes, those are the numerical variables that we have. And when you look at those variables, there was nothing like any order in them. So then it implies that we are going to use Pearson method of correlation, the small r, okay? Whereby in that case, we want to check whether there is a statistically significant relationship between these variables. And we are supposed to have it at the back of our mind that we are testing significance relationship over what? So the concept of dependency and then independency will set in. Whereas I say that when it comes to Candor or Spearman's, we mostly use these ones in case our variables have an ordinal in nature. Ordinal means that there is some order. So at the end of the day, you're going to rank and check the differences between the corresponding variables. The good example of the kind of data where you can apply the Candor or the Spearman is the Likert scale data. I don't know, for those who have done surveys, I guess you've come across this particular type of data set. And because most of the time, maybe you're asking about the level of satisfaction, agree, disagree, provided is something ordinal in nature, satisfied, non-satisfied, less satisfied, and so on. That is the kind whereby data has a certain order in it. Okay, so I'm going to stop here, go to the chart and ask, can we proceed to R now? If the little background of the theory is clear to you. they need to install HMISC package. Maybe we can put it in the chat. Okay, I'm stopping to share this. Then I go to R. As we move on to R, I kindly ask you, go to your R and then import your diamond dataset. Because we need to run it again, you have to set your working directory. Remember, we had saved it as lab2 underscore data. One of it had a CSV. Another one had an extension of an Excel sheet. So either way, whatever data set that you import in R, it will still support us to do the right analysis. I remember in the materials that I sent, you already have the bivariate.r script. The bivariate.r, it is a script that I named the work that I want to do on correlation coefficient. But remember, it's just a name, so you can change it, because I saw a question in the chat that was asking that what about expo P1 mean when Professor Susan was sharing. Okay, remember, each time you're going to run your project or your data, in case all the packages have been installed, when you move on, you don't, for example, the following day, you do not need to install these packages again. All you need to do is to load them by using the library command. Just load them and then continue. So what we are going to do, we are going to load our packages. So as I work, I also ask you that you can work alongside me. I already have, I've already sent you this particular script, the bivariate.r. So I'm going to load my packages. I don't need to install them again because I installed them on Monday, so I don't need to do it again. So I'm going to install the packages that I will need, and we went through what is the relevancy of each particular package that we are having. For us to run the R call matrix, the correlation matrix, you have to have installed the HMISC package. So I'm going to ask in the chat if you've successfully loaded the packages that we are going to use. Okay, great. Now let's move on. The next step is we need to import our data in R. We are using the same data we had on day 1 and day 2 because what we covered before, it was just descriptive. Now we are moving on and then see. Let me leave you to import data in R, because right now I believe that you've learned that skill of importing data by using the setwd, set working directory, because the set working directory varies from computer to computer. And so it is always unique on your computer and it's different from the rest. So I'm going to import my data in R. Okay, after importing my data in R, remember for my case, I'm still using the same object name, diamond. And for you to confirm that you've imported it right, you have to check in your environment and see that, for example, when I look at my environment, it shows me that my diamond data has got 100 observations and 7 variables. And at the same time, when I look at the console, the R console, where the commands are executed, I don't see any red mark or a warning. So that one tells me that I've been able to successfully import my data. I'm going to ask in the chat whether you've done that particular step. Have you been able to import your data? A question that, how do we import bivariate? That's an interesting one. We do not import bivariate. Bivariate means two, that on your data, you're going to see the relationship between 2 variables. But we're using the data that I sent you earlier, the lab2 underscore data. Let's import that data and then we continue with the analysis. But we are not importing bivariate data of the sort. Somebody saying that I don't have the diamond data. Kindly check the lab2 underscore data. Yes, the lab2 underscore data, it was saved in two ways. We had the one that had the CSV and the other one that was saved as a normal Excel sheet. And we learned how both of those two types can be imported in R. For my case, I'm using the one of read.csv and I'm giving it an object. We are using a script code by variate.r. Sorry. Diamond is not, diamond, it's a name that I gave to my data set after importing it. It is an object. And in this particular case, if you don't want to name it diamond, you can change that particular name. Because I named it diamond, I don't want to keep changing it. Import your data in R and then give it any name that you want. Because why I said that I assigned it to another name, like I cannot keep on recalling my working directory because the path is very long. So I thought that I could look at something that is short that can support me when I'm doing my analysis. Somebody is saying that I've imported the original data lab2 underscore data. Yes, it is the one that we are using. Exactly. We are using the same data set. Please import in your R Studio and open that particular script. Unless the data is imported successfully, then it implies that you will do the right analysis. If you fail, then you will be disappointed and get discouraged. So I'm going to ask again, have you been able to load your data, the lab2 dash data in R such that we proceed? Great. If you want to clean the environment window, we use the remove command. Okay. But remember, the moment you clean the environment, it implies that whatever you've loaded, you've cleared it, you will not see anything. Then you have to load it again. So for that one who is asking, how can we clear the environment? You go in your console, move to R console and type RM, which means remove. Inside, you type list, which is equal to ls. ls gives you the list of objects that are within the environment. For example, diamond is an object that I've created. Any object that you create, it is saved in the environment, you'll see it as a list. So now, the moment you click RM, you're telling R that remove everything in my environment. So the moment you enter that, then it implies that your environment will be clean. I don't know if you're seeing my environment, it is now clean, and you can do the same. Okay, somebody's joining for the first time. I kindly encourage you that you follow our YouTubes for each day such that I'll get on the same page. All right, given that I've cleaned my environment, then R doesn't know that even I created the what? That if you want to clean the environment, all you need to do, if you're seeing my console, that is the command I'm using, the one that I've highlighted. It has RM. RM means remove. I'm using the RM command. And inside the RM command, I'm telling R that list is equal to ls. List is in short term in R, it's ls. ls lists the different objects that you've stored in the environment. So when the moment you put RM, you're telling R that remove all the objects that I've created in my environment. And so my environment will be now empty. Okay, you can type that in when you want to clear environment. But the moment you clear the environment, remember to redo everything again, because now you've cleared the memory. All right, so I'm going to move on. I'm going to reload my data again. It is the same. Okay, I'm going to import my data again, like we did earlier. So, and then that is my working directory. Remember, I looked at setting a working directory on Monday. And then now I use the read.csv command to import my data to R. So when I import my data, remember, this is an object name. Diamond, it's an object name. I can put Helen, I can put Susan, I can put anything. I just put Diamond because it was directly, there was a direct relationship with the data set, such that my mind gets, my mind keeps on remembering that, okay, and I named my data set Diamond. So it is an object that I named it. It is what they're having, I didn't edit. It's too long. Which file? Which file? I don't get you. Okay. Okay. I'm going to, some of you are saying that you don't have the script. So what I want to do is to paste the R script again in R. Yeah, I've sent it now. Please get it in the chat and then download. What I'm using is what I've sent you, such that we are on the same page. Download, and then we follow through together. Do we import the Excel or CSV set? You import any that you want. You can import the one of Excel, or you can import the one of CSV. And I remember vividly clearly that we learned how to import that too. But for now, pick one. Okay, let's move on. Within my data set, since I'm going to, like I said on Monday or on Tuesday, that it's always better you first take a clear look of how your data looks like, okay? When, whether you, on how, such that it gives you a familiar look on what you expect to do at the end of the day. So most of the time, you start by looking at the structure of the data. I'm told when you look at my console, there is a command, there is an error that most of you are getting, which says error in str demand. They're telling me that object diamond not found. Why object diamond is not found? Because I did not, after setting my working directory, I just stopped there and I didn't command R to bring the data that I want. So I'm going to go back and run the command for diamond that I want, and then diamond. Now I've gotten the diamond. When you check in my environment, now it is showing that I've successfully imported the diamond data, which has got 100 observation and 7 variables. We said when I run now my structure, we saw this already. It just shows you how your data looks like, level of measurements. You can see whether you can tell out that certain variables are factor in nature. You can use as a factor, or you can use factor. Still, that question has been popping up so much. All right, now let's move on. This part of descriptive by groups, I'm going to be a little bit fast because you've already looked at it with Professor Susan, and I guess it is still a similar explanation that you have. All right, now, when you want to group by Remember, it's supposed to be a categorical variable and a continuous variable. You know, yes, Prof. Susan is looking at experimental data. Whatever that I am doing, it is done in case you're having survey data. But most of the time, what might be different is how you explain your data, but sometimes the commands are the same. So we use the group by command. If you're seeing my screen properly, we use the group by command. What are we grouping? I tell R that go to my data diamond that I've got it. I want to group quality. Quality is my factor. Quality, whereby for it had 5 categories. It had fair, good, premium, very good, and then ideal. Those were the labels of quality. So it is categorical, and I've told R that it is a factor, all right? And now when I move down, you remember clearly when we use the dply command, it supports us in data manipulation, all right? And different operations that we want. So in this particular case, I'm telling R that I want you to summarize for me. I want you to give me the count. Remember now, I'm moving on to, I want to group quality by what? I want to group quality by its length. You group a categorical with a continuous. That is when we use a group by command. So in this particular case, I'm telling R that summarize for me. I want to get the count. The count of quality. I want to get the mean length of the different levels within quality. At the same time, the standard deviation. Some of you are asking, what about getting the SD? But it's about how you manipulate these particular commands and put in what exactly that you want. And it is always important that you use the help command. Okay? Professor Susan talked about the pipe operator. It's like you're putting different commands together, but all the things can be done separately. The na.rm, that one it implies, in case you're having missing variables, sometimes you go to the field and collect data, but by the time you reach on the table, maybe some of the responses are missing and they are not there. So in this particular case, good enough, the data set that we are using, it doesn't have missing values. But in case you're having any data set which has got missing values, then you use the command na.rm. Like I said earlier, that R is remove equal to true. That give me the mean of length that corresponds to quality, but do not consider missing variables. But good enough, we don't have that. So when I run this in R, remember our codes are executed in the R console. We do the coding in the R studio, and then we see our results in the R console. I mean, look at this, look at our output. I'm taking a quick look because this is what you've just done, and we're just transferring information from what you've learned from experimental data and what I'm having here. In this particular case, my quality had fair, good, ideal, premium, and then very good. However, I asked R to give me the count, that now the count is the same as the frequency. The number of those that are fair were 5, those were good were 8, those were ideal were 39, the premium were 35, and the very good were 13. And I tell R that group the quality and give me the length. So by the length, I want the mean length for quality. So the length for 5, the mean length for fair diamonds is 6.08. For good, it is 6.66, and so on. And then they're also giving us the standard deviation. The standard deviation for the diamonds that are fair, it is 0.731. For good, it is 0.777. And so on. This is what you've just looked at with Professor Susan. So I don't want to really drag there so much. We are using the same thing. Yes, she talked about how to use the palette, whereby palette is about, it talks about different colors in R. So that one shouldn't perturb you. The moment you find like there's a palette, it talks about how do you derive different colors within R and use them when you're doing your graphical analysis. And it's quite interesting to note, like from the previous presentation, Professor Susan mentioned that when you're writing a publication, you don't need the colors. Most of the time we use black, but when it's varying in shades, when you're writing your publication. So I use, in case I want to represent this in a pictorial form. So I'm going to use a box plot, a GG box plot, which you've already looked at with Professor Susan, still in what she has just presented. In the chat, I saw somebody was asking, why don't I use a scatter plot instead of a GG plot? Please, as you're working out your analysis, always you have to have it at the back of your mind that why am I using this? Why aren't I using a scatter plot? Why am I, in this case, using a GG plot? Because the moment you get the basic principles, then you'll be able to, like, even if you get to any data set of any sort, you'll be able to do the right pictorial. So in this case, we are using a box plot. I open the GG box plot command. Okay, it is the one that I'm having here. It is always good to use the help command. It is inbuilt within the R programming language to support you to get all these particular arguments. If you feel something is not clear, all you need to do is to type help, okay, help, and then inside help, you put in the command that you don't understand, and then they will tell you that in case you want to do a GG box, this is what you're supposed to do. So you can say GG, then box plot. Okay, and then the moment you click enter, all you need to do within the R Studio, you run it. When you come to the R console, you enter. Okay, in case I run that, you check on your right-hand side at the bottom, and then they'll give you clear descriptions on what is being entered. That, okay, within the GG box plot, first I need to put the data. This is what we are doing. How do we use, somebody was asking, how are we going to get these particular commands? You can get all these commands by using just a command help. I want help on a histogram, help on this. They'll give you a usage command. How are you going to get what you want? So within my GG box plot, they are telling me input the data. Look at in my command, I've got diamond. The next is X. What is your X variable? What is your Y variable? My X variable is quality, which I want to which is categorical. And then my Y is the length. You can tell you that, okay, what color? I picked palette. Now, when you come to the usage here, the moment that you see now, it implies that you can leave it in, you might use it or you might not use it. Most of the time when you check the help command, pick only what you want, and then you put it in in R, and then leave the rest. So in case I run this command, okay, when you check, I'm wondering if, let me check in the chat. Are you seeing the zoomed plots? Are you seeing the zoomed plots? Not zoomed. Some are saying yes, some are. I go to show. Okay. Okay. Okay, what about there? I think I've zoomed now. Okay. The best things, like what Prof has just explained about the box plots, you have to look at, it is a 5 summary. I'm going to just give you a summary because you already have these particular details already. It's a 5 summary. You can use the box plot to measure the variation and check in case maybe there are variation between the different categories. And then at the same time, you can check which of the box plot can, the one that maybe stands out than the rest, and you do the different measurements, checking the variation. And at the same time, you can be able to tell within a particular box plot of a certain category, whether the data is normally distributed or whether it is skewed at the left or at the right, and then you make all those particular conclusions. Okay, So this one I'm not going to do to waste a lot of time because a lot has already been said about it. All right. Now let's move on. Within the R script that I've sent you, now we are moving on to correlation. That was just, let's move on to correlation and see. I'm still using the same data set. When you move on to, as you scroll down, whatever you see that is green within my script, those are just comments. Comments I made, they are inactive. R doesn't run them. They seem inactive, but they're just put as reminders such that in case you come back next week, you just read through your script and it gives you a quick reminder of what exactly that you are supposed to do. Now, I can also use a command, gscatter, okay? And now remember, I'm moving on to correlation. Within correlation, I'm going to consider two variables. I'm going to consider weight, I'm going to consider price within my diamond data set. The reason is, the previous days we are talking about how you can tell, how can you tell that my variables are dependent on a certain variable and so on. For example, when most of the variables can be measured, then it implies that it will be easy for you to see that the error would be very minimal because you do the measurements. And then, and where you see that on some other thing whereby if you're trying to measure, but the randomness is very big or there are high chances of having a big error, then it implies that other variables will act on that particular variable. For example, in this particular case, I'm going to consider price as my dependent variable because it is influenced by many things. When you look at it practically in the usual setting, price is influenced by many things. And now in this particular case, if you look at diamond, price is influenced by weight, it's influenced by the depth, it is influenced by the length, among others, like that. So when I come here, I want to, from the plots that I showed you already, I can use the gscatter command. Still, this command I can check within help command, and it tells me how do I use this particular command such that I manipulate it according to my data. Okay, I put in the diamond, which is my data set, my X value, which is my weight, and then my Y, which is the price, the dependent variable. However, I tell R that please add a regression line. So I say add equal to reg line. And then I tell it also put confidence intervals. And I write conf equal to true that indicate them. And I also tell it indicate my correlation. I indicate it to be true, that I expect on my graph to see the correlation on it. And then I also tell R that the kind of correlation that I want to do, because both my variables are continuous, I want to use a Pearson method. So I come here, call method is equal to Pearson. I can label my X, the X axis, and then the Y axis. So at the end, I run it. Okay, the moment I run, this is the output that I get. Okay. What happened? I'm having trouble. I want to share it. Okay. I want to share the, no, that's not an error. Now, when you look at the plot it's a scatter, that I just scatter plot that we have gotten. When you look at this, we've got price and then weight. It's quite interesting that we are seeing a positive relationship because as the price increases, our weight increases. And then still further, R goes on to tell you that my correlation coefficient R is 0.92 and my P is 2.2e minus 6. Most of the time when we are reporting this data on correlation, there are two things that you're supposed to put at the back of your mind. You're reporting the correlation coefficient and also your p-value, the level of significance, because most of the time statistically, we look at this more probability to be as 0.05. So in that particular case, any figure that is lower than that, we say that those two variables are correlated, and we either say strong or not strong or weak, depending on the value of the correlation coefficient. So this is what we are having. I'm going back to R. Please answer that. Thank you. So now let's go on. Now, I mentioned that we can use the call test. This is the test, call.test. And in case we don't want to, we just want our results directly. And within the call test, all you need to do, you tell that I'm using my X variable, which is weight, and then my Y variable, which is price, that go in my diamond data set and pick for me weight. That's why there is a $sign. Go in my diamond data set and get for me price. So that is diamond price. And then you say, I want to use the method Pearson. So, but I created everything in an object called as. It was association, and then I only picked the first three letters, because whatever that you do, you attach a meaning. In case I run this, see, I've gotten another object in my list or within the environment. And for me to see the output, I need to run the object. So when I run that, this is the result that I'm getting. When you look in my R console, I'm told that my T statistic is 24.033. The degrees of freedom is 98. And the p-value is the same one that we saw earlier, which is 2.2e minus 16. So that is like 0.0006 up to 16 and then 2.2. And it goes ahead to tell you the confidence interval, that my confidence interval lies between 0.89 and 0.95. That is the lower and then the upper. And it also further tells me the correlation coefficient, which is 0.992. So now we need to understand, how do you specifically state out this particular result? The one thing that you've noted in mind, that in case for me to see if there is a statistically significant relationship, my p-value has to be less than 0.05, which is what I'm seeing on the screen. At the same time, I am saying that my correlation is 0.92, which is a strong correlation because it is tending to 1. So what should come at the back of your mind is that given a strong correlation of 0.9 between weight and price, and so I can confidently say that there is a strong statistical relationship between price and diamond, with my p-value equal to 0.0.0. Okay. I'm going to go in the chart and ask, is what I've explained clear? Is it clear? Okay, and let's proceed. I'm just going to make a quick recap such that we are on the same page. I said in case you want to run a correlation test, all you need to do is to use a call test command. Within a call test command, you first indicate your X and then your Y. My X is weight, my Y is price. And then also, okay, sorry about that. And then also, I indicate the method I want to use. Now I told R that I want to use the Pearson method. Why I've told R specifically to use that? Because the two variables are continuous in nature. However, we say in case it is a different kind of method, then all you need to do is to edit this area and then put in what type of method of correlation that you want to use. All right. When I ran my output, this is what I came up with. Somebody is asking, what is us? Us is an object. It was association, because at the back of my mind, I know that in case I want to look at a correlation, I want to look if there is a relationship between two variables. So instead of writing the whole word, I just pick the first three words. It's an object. Like we say diamond was an object. In case you feel us is not right for you, you can use another name. You can use, maybe you can write the whole term association or Pearson, because at the end of the day, these are just objects that can be changed every now and then. So my output, the moment I run this particular command, in case I run that command as, okay, which has got the correlation command in it, it doesn't give me the output because I've embedded everything within us. So I need to come and type the object and such that I see my output. So the moment I run that line, it will give me now what is entailed within the object that I've said. And in this case, what I'm seeing, it tells me the method on the top that it was Pearson, and then it gives me the t-statistics. It tells me the degree of freedom, the p-value, my p-value, because I'm going to use my p-value to decide whether I reject the hypothesis, whether I say there is a relationship or there isn't any relationship from my p-value. And then it goes further to tell me it tells me the confidence interval, and at the same time, it gives me the correlation coefficient R, which is 0.92. Okay, so now in this particular case, now when you're explaining your result, all you need to report it's about your R, the correlation, and then you report also about your p-value to inform the reader that, you know what, when I look at both weight and price, I'm seeing statistically, they are statistically related, because my p-value, the probability to check whether the null hypothesis is as small as possible to be correct, it is less than 0.05. And in our case, we are having 0.0 up to 16, then 2.2, which is really, really very small. So in that case, we reject we will accept that there is a relationship. I'm asking the chat, is it now clear? I proceed. Kindly type yes. Okay, fine. I'm moving on. R equal to 0.92. That is our correlation coefficient, R. That is the 0.92. So for that one, it shows the magnitude. Remember what we said earlier when we are seeking two things, the magnitude or the strength, okay, of the two variables, and then the direction. So in this case, that is what R tells us. The magnitude or the strength of an association between price and weight. All right, having gotten that, when you check in my R script, there are even more detailed explanations, so you can borrow from there. Now, lastly, I want to talk about what does E minus 16 mean? Okay, that one is from when you look at our p-value, we are told that it's 2.2 e to the power minus E16, minus 16. It is the same as saying that is 2.2 times 10 to the power minus 16. It is just the language that is just missing here, but it's the same as 2.2 times 10 to the power minus 16. All right, let's move on. Now, the last bit I want to talk about is the correlation matrix. Let's try to move on with a little bit of speed, such that we move on to regression, because I want to end this particular part, and then tomorrow we'll start on something else, given the time is running out. All right, now let's move on. How about a correlation matrix? We said with a correlation matrix, you can have many variables. You can run many continuous variables together and check whether they are corrected in one way. So what I'm going to first do, I'm going to go to my diamond data set and remove all the categorical values, because remember, when I'm running a correlation, I need continuous values. Okay, so this command, it is going to help me to remove. Remember when we're doing data manipulation that you can add a column and you can reduce. So in this particular case, you can add a column, and then you can minus a column. How do we minus? You can use the select command. So what I'm going to do, I'm going to create a new data set. This new data set, I'm going to call it Diamond 2. Such that Diamond 2 contains the data that I need without color and without quality, because color and quality are categorical in nature. So since I'm running correlation, I want to remove them from the data set. But for me to maintain the previous data set, I can create a new data set by creating another object, and then I use a command subset. We did this in data manipulation. Are you seeing my screen? They're saying, Prof, are you seeing my screen? What about now? You're seeing my screen now? Okay, great. Thank you for that. Now, as we move on, remember, I want to do a correlation matrix. I want to check whether the continuous variables that I've got in my data set are correlated in some way. However, within my data set, I've got categorical variables. So I want to remove them, to put them aside, such that now I only look at a data set which has got only continuous variables. We looked at that in data manipulation on Tuesday. So what I do, I create a new object. I call it Diamond 2. And I say, I use the subset command, which we learned on Tuesday. I tell it that go in my Diamond data set, what I've been looking at, what I've been using all along, and then remove color and quality. We said C it is to bring together, to concatenate. And the moment I put a minus in front of concatenate, it implies that do away with these two. You can even put as more as you can, depending on the variables that you collected. So the moment I run, remember in my Diamond data set, I had 7 variables. So in case I minus by 2, it implies that I'm going to remain with 5 variables. I'll run that command. The moment I run it and I look in my environment, look, I've gotten another list of objects, which is called Diamond 2, with 100 observation, but this time around with 5 variables. And I can even go ahead and view it and check whether those ones have, the 2 have gone away. So instead of displaying the whole data set, I can use head to see the first 6 rows. So when I type head, I'm able to see, now look at the new data set I'm having. I've only asked R to show me only the 5, 6 rows. So now I have weight, price, length, width, and depth. The color and quality, they are no longer there in my new object that I've created, which is what? Which is Diamond 2. So now I'm going to use Diamond 2 to run the correlation matrix, because now these ones are continuous in nature, and so I can use them to run a correlation. Remember what we said, we run a correlation matrix if you're using more than one variable. So there can be many of them, multiple variables. Okay, so I use a command call in R. So still, if you want to get more information about call, type the help command, it will give you more details. However, this time the call, I'm using it on my new data set. I'm proceeding. I've created a new diamond, a new object called diamond 2. I'm explaining this line here. I've created a new object called diamond 2, but I want in my diamond 2 not to have variables that are categorical in nature, because I will not be able to do the correlations with them. I'll use a different test statistic. So I tell R, delete them out. By using, I say subset. Subsetting, it's like I'm picking from the big one and from the whole data. But now only pick for me these variables that are the ones that I want to deal with. That's why I use the subset. And then within my diamond data set, all right, go and select only color variable and quality and remove them. That's why I'm putting a minus, such that they do not appear in my new object diamond 2. And it's the one that I'm going to use now as I continue. I'm going to ask in the chat, have you gotten how to remove have you gotten how now to only come up with only continuous variables in diamond 2? Okay, wonderful. In case you can't find diamond 2, then it implies that there is an error somewhere that you have to check. But diamond 2, I've created it from diamond. However, with diamond 2, for it doesn't have categorical variables. Okay, so now let's proceed, since I'm seeing a lot of yes. So we run, I'm using the call command. When you look at my console, what is showing me that the call, now I'm using diamond 2. Since I've put it in an object which I've called res, R-E-S, for me to be able to see the output, I need now to run my object. So when I run, are you seeing what I'm getting? It is giving me the different correlations, the correlation coefficients of how the variables are related. You will check within our output and see that in case you're looking at a correlation coefficient between the same variable, automatically it will always give us a 1. You just look here, between weight and weight, it's 1, then price and price is 1. However, when you want to check whether there is an association between, you can check between price and weight. We already have this. I'm looking at this price and then weight. This one we've already got, it is 0.92, which is a positive and strong. When you continue and check between price and length, it is also showing us that it's 0.89. When you move on between price and width, it is 0.9. These are our correlation coefficients, but now we are looking at how our continuous variables are related with each other, and more so on the price, which we say that it is the dependent that is being influenced by these other variables, the weight, length, width, and then the depth. Okay, in case you want to have a more clean, in case you want to reduce on the number of decimal points, what you do, you go and use the command round, and then round your object, the rest, and you ask it that I want it to 2 decimal places. So when I run that, you see the output that I get. Now it has truncated to 2 decimal places, such that it makes me to read my values very clearly. Okay, so now I'm going to move on now to the last bit here, which is the correlation matrix. Okay, Barley, what you've typed within the chat is also correct. Continue. Yes, it's the same thing. So when we continue with the correlation matrix, what I'm going to do, remember I told you, you need to run the library HMISC, such that we are able to run the correlation matrix. And this one, what it does, it gives us the correlation coefficient and at the same time, the p-values. to check whether there is significance among these variables by checking if our alpha or the p-values are less than 0.05. So I use the rcall command, that one there. Within the rcall command, what I do now, the other thing that I'm going to do, because there are multiple variables, there are many of them, I use another command I inserted there, which is the as matrix. Okay, I want it to look, it's going to be a matrix of the output that I'm going to get, but I want it as a matrix of what data set, of my diamond 2 data set. And this is what this command is all about. And I run that. So when I check the output of now, remember, this is my object. I said objects keep on changing depending on what you want to assign it to. So now to see the output, I'm going to run. What it shows me two things. It shows me the correlation coefficient within the upper part, and then the downer part, it shows me the p-values. Here, these ones, we've already looked at them earlier, but with the correlation matrix, we get two things at a go. The correlation coefficient, which shows us the strength, and then also the p-values. However, as you look here, because we are getting that all our p-values, the relationship between these variables, it is 0. So everywhere it is 0. But this shouldn't be the case, because sometimes you run another analysis whereby maybe it can give you like a 0, whereby your p-value is not 0 or it's not significant, and it could be above 0.05, which as we run off, that we are going to encounter. So I want to stop here and go to the chat and ask if we are on the same page. And if there's something that is not clear, I'll be happy to answer that. So have you gotten how to do a correlation matrix? Oh, great. I'm seeing that we are having a very good class now, that we are picking things on the same pace. Wonderful. Now that is the little bit that I wanted to share about correlation, because most of the time it's important when you want to look at how these variables are associated to the other. So I'm going to stop here and then move on to regression. Is that okay? Or I give you a 2-minute break? I want to give you only 2, and then we'll switch on to linear regression. Yes, we can. Like I said, as we get advanced in R, all the things you pick a package, you eat a little by little. You don't eat everything at a go. But by the end of the day, you will be very good. Like these things will be part of you. It is possible to transform a correlation into a pictorial form. So I'm giving you only 2 minutes, and then I switch on to linear regression. I'm glad that I've been able to pick that particular concept. Like Nana is saying, it requires constant practice. That is very true. The more you practice the things, the more you get familiar with them. The more you get the errors, the more you get to learn how to solve them. Because part of the journey as you're doing any programming language, errors will be there. But each time you see an error, it sharpens your brain because you need a solution. So the more you use it, the more you'll get a solution on how to go about a certain error. Okay, I'm giving you 2 minutes, and then I continue. I'm going to be looking in the chat if there's some things that I can clarify. I have to wait for. How can I use R to clean the data? How do you clean data in R? These are the things that is the other term that you can use is data manipulation. So you either In case you've got missing variables, you can remove them, you can add, you can code, you can create, and so on. Can you rehearse the last part? Goodness. It's what it. It's sorry,
Ellen,
I
you're
was muted. Okay. Yes, somebody was asking about the difference between that I'm not seeing the Diamond 2. Diamond 2 dataset was created as it was a new dataset that I wanted, such that I do away with categorical values, variables, because remember, I wanted to run multiple values into a correlation. And in that case, I needed to remove the categorical values within my main data set. So I created a new data set that I named Diamond 2. You can also give it any other name, but it was about manipulation. Like I said earlier, you can have a big data set and then you can have different portions within this data set, but to enable you to do your analysis very well. For example, in case you're within agriculture, you can say, I'm going to first run analysis using plot 1, then I go to plot 2, then I go to plot 3. So that is what we are doing, subsetting. All right. In that particular case, you can't use a pipe operator. The pipe operator is used for your information just to add different commands together. That's when we use a pipe operator. You can use a pipe operator if you have, for example, you might want to put different commands within one line. That's when you use a pipe operator. But that one doesn't mean you cannot run these separate commands separately. Because within R, as you get advanced in R, you will find that you might not need even to break these commands that you have, and you can put everything together. So when it comes to, in this particular case, we don't do that. Res2 is not found. Res is an object that I created to support me to get the correlation matrix. It's an object that I named. You can name it anything. So in case you want to see its output, you have to move on the second line and type res. Okay, I'm going to go in the chat and ask, can we proceed now to linear regression? All right. Okay, now let's move on to linear regression. I'm going to take you a little, when we are running linear regression, it is always good to understand a little bit of the theory, what is entailed there. So I'm going to just briefly go through just few slides, not the mathematics per se, but just to support you understand what we are going to do in R, because it is one of the commonly used statistical tests within when we are analyzing data. And so we are supposed to know, when am I supposed to use linear regression? Because whatever test that you use, you're supposed, from depending on your data, you are supposed to check the right test that you're supposed to use. Okay. That what? Yes, which noise? Okay. Okay, let's proceed. Briefly, we are going to understand what a simple linear regression model is. How can you define a good model, multiple linear regression, hypothesis testing and confidence interval, and then now we move into R. This is just a hint, brief. I'm going to go everything in a brief. However, just have it in the back of your mind that we are teaching linear regression, it can even take a full semester and beyond, but we're only picking the main key things. So what we need to understand is that when you're going to perform as a regression model, what should come at the back of your mind is that we use regression models to be able to predict a response for a given data set of our predictor variables. A response variable, it is the same as the dependent variable. And the predators are the same as the independent variables or the explanatory variables. So we need to understand, what are we predicting? We are predicting how the independent variables are affecting our response variable. In the diamond data set, we are considering price as our response variable and the other variables that we have as our independent variables. So we check how do they predict how do length, price, how do length, width, weight predict price, among others. So it's supposed to have both an independent and a dependent. And in this particular case, the dependent variable should be numerical in nature. So you have to note at the back of your mind, in case your dependent variable is not numerical or is not continuous, then don't think of using a simple linear regression because you'll be getting wrong results. And for a simple linear regression, for it to be simple, it implies that you only have one independent variable that is affecting the dependent variable. Whereas with a multiple linear regression, it implies that you're having more than one independent variable affecting or influencing your dependent variable. That is the difference between simple and multi. With simple, one variable, one dependent variable. With multi, more than one dependent variable. Okay, now it's always good to understand how does a good model look like? Usually, a good model must be very simple. It should have at least very few variables. And at the same time, this particular model should be able to explain at least 75% of the variation within the data. When you look at my screen, I showed some examples on how a good model can look like. When you look at the first one on your left, we are saying that my line of fit can quickly fit properly within my data, and it moves in the positive direction. The same to the one in the middle. But when you look at the one at the extreme right, there is a lot of variation from the line of fit. So that's why I'm saying that this one is not, it's bad. It's a bad model. Okay. Now, for a simple linear regression, I don't know how, for us to clearly put it more direct, if you remember, the simple thing is as how to write a line. Is it a line that y is equal to b plus mx? So is it that? Okay, yes. If you remember how to write out a model of a line whereby y is equal to the intercept, then plus the slope, and then the x variable. It is the same thing, the same idea that we are putting here. So this is how I write out my simple linear regression. I've got my y, which is equal to beta naught plus beta 1x plus epsilon. Okay, and in this particular case, what if you've heard of about the equation of a line, yes, that is the term I was looking at. The equation of a line, which is y is equal to a plus bx, whereby one is a slope, an intercept, then a slope. So it is the same idea that we are transferring here, whereby my beta naught, in the usual term, the one for equation of a line, which is b naught, it is my intercept. And then my beta 1 we call it a slope, but within a regression, we call them parameters or a slope parameter, okay? And my y is my dependent variable, my x is my independent variable. So in case I increase the value of the independent variable, remember I said that is something else. But in general, beta naught and beta 1, we refer to them as regression coefficients, and we determine them from our data. The most commonly method used when you determine these particular coefficients of your model, most of the time we use the method of least squares and then the maximum likelihood. And within the method of least squares, we are trying to minimize the sum of squares with the sum of errors within the within our model. Because the more we reduce the error within the model, the more it helps us to, the more it will tell us that we've made a model of a good fit that clearly fits our data. Okay, and in case the beta nodes and then the B1s are known, then it implies that now we've completely described our data. Okay, I'll give an example. I was checking here that I'm only going to talk about the least square methods, but I'm not going to go into the mathematics because all what we need is to understand how do we do it in R, though we briefly need this particular information at the back of our mind, such that when I'm going to explain the results in R, they become very easy for you, all right? When you look within the least squares, most of the time, when you look at your data, here they're giving us within a sample like of X and X1 and YI. I gave a simple example here. Okay, like you're having my Y variable and then my X variable. My Y is my dependent and then my X is my independent variable. And so in this particular case, I can, because they're all numerical in nature, because my Y variable is an integer, in this case an integer, I can run a linear regression. So there's something you can see it like, now in case I go to my data, what you're seeing down here where I'm putting my cursor, this is it's just an extract I got from the data that you have, the lab 2 data. So whereby now my price is going to be my dependent variable, and then the rest of other variables are going to be my independent variables. Because I know that my Y variable, the dependent variable, is continuous in nature, or it's numerical in nature, then it implies that I can run a regression. However, there are some things that you have to have at the back of your mind, the assumptions for a simple linear regression. However much we might not probe them here. That when you want to do a linear regression, you have to check the relationship in this particular case between price and the rest of the variables. And also my dependent variable, the data set that I have, that price should be normally distributed with a mean, mu, and sigma squared. As we proceed, we need to check whether the residues are normally distributed with mean 0 and variance of sigma squared. And at the same time, the residues have to be constant. I'm going to show all these things in R, and we see how it works out. Okay, so now, it is also important as we draw to check the line of best fit that clearly fits our data. Like I mentioned earlier, we are trying to minimize the sum of squares. And this particular case, what we do, you look at the difference between the line of best fit and then the observed value. This line that you're seeing here, where I'm moving my cursor, it's the one that, which is the fitted line for my data. We're going to see how to get that. And it's Y, which is equal to beta naught plus beta 1 X. Beta 1 and beta naught and beta 1, those are my parameters that I'm going to define from the data. And then these particular dots are the observed values. And for them, they've got 100% variance from the fitted line. However, we always want to see that our data fits this particular line, the line of best fit. And you see that on the line of best fit, there are some observed variables that are there. And the length between the fitted line, or the fitted line and the observed one here, is what we refer to as error or residue, or yes, most of the time we refer to it as an error or the residue. Okay. Now, when you go mathematically, they are within when you're using the OLS, the ordinal squares. These are the formulas on how they can be determined with option 1, or you can use option 2. But I'm not going to go through into all of this. And we know that when you're we need this when you're determining the beta naught and the beta 1, and then you move on. But we are not going to go into that. Now, I've just talked about the fitted line, and then our predicted, the fitted line, which is the fitted line, and it is the one that we use to get the fitted values. The moment we are able to fit our line, then we no longer have the beta naught and the beta 1s. So this time around, because the parameters have been determined, we write them as beta hat and then beta 1 hat. And how do we get the difference between, how do we get the residue? Like I showed earlier here, we get the difference between the fitted line and then the predicted one, and then minus the observed one. So I'll get here on the regression residues. Residues, like I said, which is epsilon 1, is just the difference between the observed and then the predicted. On this particular red line that you are seeing, there are values there, there are data points there. So and then we've got also data points that are either up on the fitted line or below. So we are trying to see, so what is this particular distance in between? I mentioned that it's a residue and it's an error. So for us to get that error, it is you get the difference between the observed minus the observed point of the dependent variable y minus the fitted one, and that is what we refer to as a residue. However, you might ask yourself that is it really important for me to use residues? That yes, it is very important, because by the end of the day, we need to calculate the error sum of squares to see how are we doing, because if it is very little, then it implies that we are getting a good fit. And at the same time, we can check whether the variance is constant. And when we move further, we are going to find out how we can use the coefficient of determination. And in this particular case, our coefficient of determination, it is the one that helps us to explain the degree, the amount of data that has been able to be explained by the dependent variable. And so most of the time, I encourage you to go back and check in the different notes, or you can read about this particular expression, whereby my r squared, which is the coefficient of determination, it is equal to 1 minus the sums of square error, and also the total sum of squares. I've already talked about the coefficient of determination, which is also the r squared, and what it does. Now, what I want us to do, for the case of multiple linear regression, we include more independent variables. I want us to go to R now, given that you've gotten the brief, and then we see how does this work in R, and check, and then get clear interpretations. And the other thing, maybe lastly, within what we need to understand is that is hypothesis testing and then the confidence interval, because they also support us when we are going to make conclusion. Because most of the time is that one thing that we have to understand at the back of our mind is that after fitting my model, I need to understand whether the independent variable is significantly related to the dependent variable. And for us to do that, we are going to do hypothesis testing. Within hypothesis testing, we are testing the slope, whether they are showing any significant, whether it shows whether there's a linear relationship or not, and whether there is a relationship that in our particular case, where the price is related to, there is a relationship with weight. So when you're seeing my beta cap, these are the betas that I like, these are my coefficients, or the slopes that I want to use. And with the null hypothesis, I'm assuming that there is no linear relationship. So my beta 1, because it's beta I, depending on the beta, in case of a simple linear regression, which will be only one slope that is equal to 0. If it is equal to 0, it implies there is no relation. However, the null states that no, there might be a relationship. And this relationship, we have to test whether it's significant or not. And then now we can still move on and find the confidence interval. So I want to move to the chart and ask that, can we now move on to regression analysis in R? As Samuel, type Y is equal to MX plus C. Yes, it is the same thing that I'm explaining, you're right. I encourage you, in case you feel there's something that is not clear, kindly revisit. You can use Google and see how these formulas work. All right, I'm going to stop sharing this and then we'll move to R. Okay. Now I'm moving to R. 13 minutes. Okay, I've only gotten 13 minutes, so I have to maximize them very well, such that 917. Prof is telling me that I've got very limited time, so let me try to maximize the little time that I have. Okay, now I sent the R script, which is linear reg.r. It's what we are going to use. Okay. Are you seeing what I've shared? Are you seeing my R? Okay. Okay, let's push. I'll try to skip some of the steps and then try to concentrate on the most important ones because of the limited time that we are having. I sent you an R script which is labeled as linear reg.r. So it's what we are going to use. I don't know whether I can still post it again in the chat such that we are on the same page, but I sent it to everyone, and we can also still access it in the training materials. All right, let's move on. Remember, okay, somebody saying that I post it again. Okay, we are still using the same data set. I've posted the script again, the R script again. Kindly download it there. It's the same, we are going to use that script, but still on our data set. Damn. Okay, please download it from the chat and we continue. We are using the same data set. What is important is that I'm going to load my libraries. This one I'm very sure everyone has them already. So you see, as the moment you advance in R, you don't need to keep installing these packages again. You just load them because you already have and you don't need to have internet. I'm going to go and I set my working directory because I need to do that. I call back after setting my working directory. I'm still naming it diamond. Okay. Sometimes you can run as you're doing some manipulations. I'm sorry if I'm fast, but I'll try to slow down. It's just so I can use the plot command. Right now, most of us are well versed with what these things are because now we are using what we know already. I'm telling R, plot diamond in diamond weight with price. I want the dots to be blue, and then I can also label my title. But remember, Prof said we don't need to put a title on a figure. So we put it at the bottom. But this is just for learning purposes, but in publications, we don't do that. All right. When you look in on my right-hand side, the bottom workspace, there is a plot that shows a scatter plot whereby I'm varying price against weight. Okay, I can zoom that out such that you see it all clearly. So, professing okay. Why is it like that? It has got black, so okay. Let me just go back. Sorry. You can see the screen, yeah? All right. So let's proceed. When I continue, at the same time, I can also tell R, I'll encourage you to go and practice this particular plots. You can also tell R that as you plot out, you can also put for me the line. And I run, and I do that in the scatter.smooth command. I put my X, Y, and then I can also put the main. When I run that, you see that in my scatter plot, I've been able to see, I'm able to see the scatter plot with a regression line. I want to ask in the chat whether you've been able to get a scatter plot and put a regression line. Have you tried? Great. Okay, let's proceed in the limited time that we have. Within the script that I sent, there are various options of plotting the scatter plot. So I'm going to skip that and I leave them for you. They're easy to follow. All those are just various options. Now let's move on to what we want to do. You'll find that in case we want to plot a linear regression, we use a command LM. We use an LM function. It is LM then bracket. In case you want to understand more details about the LM, like I mentioned, all you need to do is you type help in bracket LM, and then R will show you what to do. Okay, now in my LM, I've created an object I've called model, and then I want to use the LM command. Okay, LM command is the one, it's the one that I'm going to perform the linear regression with. It's a command within R, which is inbuilt. My Y variable, which is price, and I want to say that price is a function of weight. I use the expression that I've highlighted. I'm reading it as false, or is a function of weight. And also, I go ahead and tell R that I'm considering the diamond data set. So after that, I come at the end and then I run. The moment I run, I don't see the output immediately because what I've said that I've created an object called model. So what I can do, I can either run my object or I can run my summary of the model. So when I run the summary of the model, check what happens. When I run the summary of the model, this is the result I'm being given. Okay, on looking at the output, first I'm given the residues, which is a file summary point. We've talked about it earlier. And then, but what is most important is to understand my correlation coefficient, all the different slopes that I have. Remember, I've used a simple regression and I'm also considering only weight, okay? And this is my coefficient, or the baseline, whereby my beta naught is equal to 0. But sometimes it's always important to understand that does really my intercept make sense? Because in this particular case, my intercept, it is a minus 2.112. Looking in terms of price, does it really make sense that I can get a minus price? Because when I look at it, doesn't give me any sense. I can do away with it from my explanation and then go on to understand what the other slope implies. You will see that on my slope, my beta 1, okay, I'm given that it's 7456.8. So what does this slope tell me? I'm going to ask in the chat if somebody can tell me what it implies. I don't know if they'll give us more time because it shows that I've got 3 minutes. Somebody in the chat? Yes, if they can add us like 10 minutes and I complete, please. 10. Talk to David. I'm sorry, I'm begging for more time. Yeah, okay. Yeah, I'm asking somebody in the chat to tell me what 7456.8 means. Positive correlation with price. Okay. Y intercept. The 745.6 unit cost positive correlation. Okay. A unit increase in weight. All right. Wonderful. Thank you so much for the contributions. So now what this one implies, remember this is a slope, okay? And we are saying that my weight influences the price. So I'll read this as that a unit change in weight, in case weight increases by 1 unit, then it implies that my price will change by this value, 7456.8. And I'm glad that most of you, okay, I'm glad that most of you have given me the right explanation. Thank you so much. That was a good one. So these are my coefficients that I start with. So when I look at this particular slope, I didn't look when I didn't consider the intercept because it wasn't make any meaning. And a unit increase in weight, it will change the price by this particular value, the 7456. And now when we continue further, we are having the standard error, the t-values, and then the probability. So now it is always important to check, looking at what I've come up with my p-value. On weight, it is less 2e to the minus 16, which is the same as 2 times 10 to the power minus 16. So in this particular case, I need to understand, in case I am to see whether there is a significant relationship between weight and price, the first thing that I've seen is that my p-value is less than 0.05. So that one, first of all, it implies that even the value that I'm getting is far less than 0.05. So due to the fact that it's less than 0.05, then I'll strongly conclude that there is a significant relationship between weight and price. So I'll reject the null hypothesis because the one that is said that there is no linear relationship. Prof, can you interject if you don't mind? Sorry. Professor Susan is going to share more on about how this the output works. Please talk.
Good afternoon. Take off your video. Good afternoon, participants. Dr. Helen has ambushed me, you know. Okay, I was doing something else, but good afternoon. Looking at the output, she has already told you that we produced the coefficients, the estimates of the coefficient. Our intercept is negative. Our slope is 7,456.8, which is the change in price for every unit change in weight. And from that output, we also look at, if you go across weight, I'm using the screen for Dr. Helen. We shall see a p-value, which is 2e minus 16. That means 2 times 10 to the power minus 16. Now, you remember Dr. Helen talked about the hypothesis. And that hypothesis was testing this slope of 7, 4, 5, 6, whether it is different from 0. And the significance level we set normally for environment and agriculture is 0.05. And even the default p-value is significance level is 0.05. That is the p-value which we assume that the null is correct. Now, if we get any p-value smaller than 0.05, then we have evidence to reject the null and conclude that there is a significant linear relationship between price and weight. Then, after interpreting that, we look at the multiple R squared. Now, the multiple R squared, if you look at your output below the significance codes, I can see multiple R squared of 0.8549. That is the R squared, the coefficient of determination, which tells us that it is the amount of variation explained in price when we conduct a regression between price and weight. Now, originally price had 100% variation, and we're looking for factors to fit so that that variation can be explained. Now, once we run a regression between price and weight, by regressing weight onto price, we explain 85.49% of the variability in price. There's also another value called adjust R squared. Now, adjust R squared, which is next to multiple R squared, it is used when you are dealing with multiple regression. You can see the value is slightly below 0.8549. What it does, for every parameter added in the model, that value is adjusted. It cannot be affected by the number of independent variables you put in the model. That is why it is a good criteria for assessing models when we are doing model building, when it comes to multiple regression. So that is the R squared adjust, and it is also telling us that after the regression, the amount of variability explained is 85.35% in price. Okay, now there is also a relationship between, you can see there is an F value and also corresponding degrees of freedom, and a p-value. You can see the p-value is actually equal to the p-value on top here where there are coefficients. So if you go along slope, you see the p-value is 2 times 10 to the power minus 16. And also below here, we have 2.2 times 10 to the power minus 16. Now, if you square the t-value, 24.033, if you square it with your calculator on your phone, you will get an F statistics of 577.6. So this F statistics is obtained in an analysis of variance table under regression. So if there is a time, she can show you how to get the analysis of variance table. If that is clear, may you also explain the degrees of freedom? Fine. The degrees of freedom shown, we have 1 degree of freedom, which corresponds to the number of independent variable in the model, and we only have 1 independent variable in the model, and 98 is the residual degrees of freedom, which corresponds to the mean square error. So I think I'll request her to produce the analysis of variance table so that you can see how those ones come up. Please repeat on what R squared means. R squared is coefficient of determination. It tells us the amount of variability explained in the response. In this case, the response is price. So after the regression, 85.49% has been explained in price. 85.49 of the variation has been explained in price. Any question? If there is no question, adjusted R squared meaning, it's almost similar to coefficient of determination, but as I've said, it adjusts for every parameter added into the model, and it is relevant when we are looking at multiple regression and want to remove some of the variables from the model. It is not affected by the number of parameters added on the model, but coefficient of determination, as we shall look at multiple regression, we see that it is inflated. As you add in more variables in the model, it goes up, it increases. Meanwhile, adjusted R squared does not increase because it is removing the effect of adding more parameters in the model. So, both of them explain the percentage of variation explained in price by regressing weight, but coefficient of determination is suitable for simple linear regression, and adjusted R squared is suitable for multiple regression, especially when you're doing model building. Model building means that you have so many factors and you want to select a few. Which one do we use in interpretation? For simple linear regression, you can use R squared, which is the coefficient of determination. For multiple regression, we use the adjusted R squared. Any other question? Standard error versus standard deviation. Oh dear. Here we haven't seen the standard error. Okay, the residual standard error, I can see it here. The standard deviation is a measure of the difference between the observed values and the mean. That is standard deviation. Standard error is a measure of precision. How precise is the mean? Has the mean been estimated by the data, by the values you have? Okay, you've collected from the field. Interpreting p-value. Okay, if you look at our p-value, it is 2 times 10 to the power minus 16, meaning it is 0.00000. Count them up to 16. Okay, if we compare it with the significance level of 0.05, which R has set as default, and it is the p-value we assume that the null hypothesis of no linear relationship between price and weight is correct. When we compare those two, we find that our p-value from the data of 2 times 10 to the power minus 16 is small. So the chance that the null hypothesis is correct has been tremendously reduced. Then we have high evidence to reject the null and conclude that there is a significant linear relationship between price and weight. I think that is good to go. If you've understood, please say yes, yes, or no, no. Okay. So I'm handing over to Dr. Helen so that she can use only 5 minutes. The rest you complete tomorrow. You complete tomorrow.
Okay. Can you hear me now?
We are not going to have a support link.
Okay, fine. Thank you. Given the time that we are given, I'm going to only show you how to do a multiple. We do the residues? Okay, let's do the residues, and then the other part maybe we'll start from there tomorrow. So it's ice. Okay.
Okay, ladies and gentlemen, Dr. Helen says that I should talk about the assumptions of regression. Okay, for your model to be valid, there are certain assumptions that we need to validate. The first assumption is that the data has to be normally distributed with mean mu and variance sigma squared. That's the first assumption. The data is normally distributed with mean mu and variance sigma squared. The second assumption is that there is a linear relationship between price and weight, or there is a linear relationship between the response and the independent variable. The third assumption is that the residuals are normally distributed with mean 0 and constant variance, sigma. The fourth assumption is that the residuals have constant variance. The fifth assumption is that the residuals are independent. So if your model violates especially constant variance and independence, then we have to look at the residuals. We have to decide whether we do a transformation. Kindly repeat the second one. Okay, I say the first one, the data should follow a normal distribution with mean mu and variance sigma squared. The second one is that there should be a linear relationship between the response and the independent variables or independent variable. The third one is that the residuals are normally distributed with mean 0 and variance sigma squared. And then the residuals have constant variance. And the last one is that the residuals are not correlated, they are independent. Okay? Do the assumptions cut across all regression analysis? They cut across both simple linear regression and multiple linear regression. Can we analyze without transforming? It depends on how the plots that Helen is going to construct look like. So if we look at the plots, if they are really bad and they are showing a trend that the variance is not constant, then we consider transformation. We can use natural log transformation to stabilize the variance. Okay, that's okay. Okay. Yeah,
I continue?
Yep. Okay, Helen, please continue.
Okay, thank you, Prof, for chipping in. Let's proceed. Now, given that she has talked about about the residues, the different assumptions of a simple linear regression, and so as we move on, having gotten what a simple linear regression is with only one variable, we are going to check now on our residues, because what is most important, we need to check whether the residues in the regression analysis are normally distributed, and at the same time, they have got constant variance. Hope you can hear me. Prof, you can hear me? Okay, so now what we are going to do in order to check that, we are going to use a command resid, the one that I've highlighted. Okay, it's RESID. And then in bracket, we put our model. Remember the model Prof has just explained. So I create an object which is model.res. Like I said, you can use any other name. So what I'm going to do, I run that. I want to check for the residues. And then after I continue, I see, because in this particular case, these are the different residues that I'm getting from my model. Okay, how they look like, because they are 100 observations. So in this case, I expect to get also 100 residues. Now, for me to plot them such that I get a clear look on how they look like, the usual command for plot, but this time around, I'm plotting my weight. Remember, my weight is the dependent variable, and how it is being influenced by the different residues. I'll use, then I have the residues for the model that I have. I can label and the Y, and then the X values. So I'll run that. And then when I look in my plot command, I see a certain plot. I can also try to put the horizontal line, and I can zoom it out, and then we take a close look. I'm going to stop sharing, then I share the plot. Okay, and when you look at the plot that I've shared, in this particular case, I'm plotting the residues against the weight. But what is quite interesting, remember what Prof has just explained, that we need to check whether the residues are the variance is constant, implying that we shouldn't see any pattern. And at the same time, we need to check for normality. But when you look at this the plot that we are having, there's something like a shape as you move across the line, as you get to the extreme end where there is where I'm putting the cursor. It's like we are getting a certain pattern like that is U-shaped. Then it implies that we need to go back and check our results again because somebody has proposed maybe you can do natural logarithm. So we can opt for that and ensure that we are having constant residues, and then we can also check whether the residues are constant. So I'm going to stop sharing this, and then I go back and we try to do a natural logarithm and check. What if we do natural logarithm to try to see that we don't see any pattern within the residue and see what we'll get. All right. I'm clicking again. I'm going back to my R. So what happens is that I'll skip some of those plots such that we get within the limited time we have, because we're about to be closed. Now, for some of you are talking about how do we do transformation. Well, how to do transformation is that we are going to go and do a natural logarithm such that we are able to reduce the noise or the variancy with how the data varies from our line of best fit. So we do that by taking a natural logarithm. So what I do, I command R that I'm going to create another column within my data set, such that that column gives me the log of weight and then the log of price. Remember, I said that we are using log as for transformation such that we are able to stabilize the variancy. So what I do, I run these two commands. We've already learned how we can manipulate data and add columns. And I can check again and check for the first 5. I can see in case I check the first 6 laws, I've created more 2 variables where the log weight and then the log price. With the instance, we want to reduce the noise or stabilize the variancy. What I do now, I rerun the model again, but this time around, instead of considering weight, I'll use the one that I've transformed and then the price that I've transformed. That's why I'm having this. And this time around, I changed the log name and I called it model LG, model log. So when I run this, okay, and then I can also go back and get my summary. The explanation is the same. We still have a significant relationship, but this time around, what is different is that this time around, our values are smaller when you look at the coefficients. And but what is important is that we want to check now our residues, because the point is that are we having a constant variancy, or what about the normality? Because the variance, because as we check for the variance, we have to ensure that it is constant. Now, in case I plot, if you're seeing my command, model log, see what is going to happen. The moment I run it, kindly look in the console, the R constant, see what is happening. It has not brought me the plot, but what is it doing? It is telling me that hit return to see the next plot. So in case I hit in case I come and enter, are you seeing, let me zoom that out and check now what, when we transformed, what happened. Okay, now when we transformed, such that we see that we've got a constant variance within our residues, this is what has happened now. We do not see any shape anymore within our particular data. So in this particular case, this is how we can check to see that the assumptions of linear regressions are not violated. Okay, I'm going to close this, and then I share my R again, and we continue. I share my R again. So, however, still in the R console, it is telling me to hit and get another plot. When I hit, I get the plot for normality. I'm going to zoom this, and then I share it again. And then we see how it looks like. For the case of normality, now in case of transformed data, I hope you're seeing my screen. This time around, what we are seeing that the data almost is on the straight line. For a case of a natural log, in case we take a transformation on the data, it's almost on our line. But in case the data points are very far from the line, then it implies that there is no normality. But in this particular case, it's close to the line of normality. Okay, I'll stop that, and then I'll share my R again. Using this particular command, it can give you as many plots as it will give you 4 plots. Then it gives me another plot which shows that for the standard normal. We know that for a standard normal, my mu is equal to 0 and my variance is equal to 1. So this is the plot that is giving me. However, what I'm going to do, I'm going to produce these graphs on one plot and see how they look like. So for me to produce different plots on one page, I saw that question was popping up so much. What we can do, we use a function, Perl, and then inside Perl, you put mf row. It tells R that print my figures in a 2x2 grid, okay? And then you can also print it as an mf call, whereby it will you also state in case it's 2x2 or it's 2x3, depending on what you want. So I'm commanding R, and then later I want to come up with the plot log when all the plots are together. So in this case, it is showing me that an error in plot.new, the figure margin is too big. What is it that it cannot fit in this particular window? It is very small. So I'm going to control and minus such that I increase my size here. Then I run again and see if I'll get my plot. So when I run again, still, I'm going to reduce again and see. Okay, I'm going to run again. Yes, hope like Prof has been telling that in case you get an error, all you need to do is to find a solution, because every error has a solution. Because the plot wind had been reduced, it was the reason why it was complaining that the figure margins are too big. So you have to first reduce the margins such that you're able to see your plot clearly. So in case I zoom this one out, I'm going to stop sharing, then I zoom it for you, and you are able to see it very well. Okay, so this is the plot I'm getting. For those of you who are asking that, how can we put different plots within on one grid? So we are having the fitted values against the residues. Remember the fitted values we are having, and in this particular case, we are seeing that there is a constant variance among our residues. That is the first assumption that we wanted to test. And at the same time, we wanted to check for normality, whereby the residues in a regression line are normally distributed. And looking at this particular plot where you're seeing my cursor, we see that most of the data is concentrated on this particular line that is running through. And that is enough to tell us that there is a normal relationship. Prof, I don't know whether if you have something to add or that's enough. Okay. I'll stop sharing this and I go to my chart and ask, was that helpful? In case of multiple, we just need to add more variables. Yes, I'll share the script. We can have a little review tomorrow as we start. Yes, like since you've gotten the script, it is always better in your own free time to get time and practice these particular commands, such that next time as these things they become a little bit clearer to you and you don't waste a lot of time. We can have a more review tomorrow. Do you have any communication? Somebody saying that it's too much to digest. Where? Kindly be patient. You're going to share. Okay. We are going to share 3 questions in the chat, because let me share in the chat and then you can click on it and receive, kindly click on what I've sent in the chat, and then we want to receive your feedback. This time around, we can, as you type more questions, what I've sent disappears. Click on the survey monkey that I've sent, and then and kindly respond to our questions. Sorry? Okay, I've also pasted it in the Q&A. So we want to get your feedback. Just follow through the link and then click. We will be able to read your responses and we shall be happy to respond. We have only 2 minutes to the end of the webinar. Please attend to our evaluation. Okay. Please attend to our evaluation. Attend to the questions that I've sent. Just click on the link www.surveymonkey.com. Then answer, we'll receive the feedback. Somebody's asking, why is it necessary to modify data to obey normality? We are going to have a quick recap tomorrow before Professor Susan sets in. So for now, please fill in our survey monkey, and then we'll do the rest tomorrow. Since we've gotten into the time for the office hour, we are not going to have office hour today, but we'll be happy to respond to, in case you have different questions, maybe you can send an email. You've seen the link? Please fill in the link. We'll be happy to receive the different responses. We are not answering more questions. We want to get feedback from you. Girma, please fill in our our SurveyMonkey questionnaire. Yes, it is okay. You can use our emails. Mm-hmm. Mm. Okay. I think that marks the end of today. It has been a great journey. This is our 5th day, and we are going to meet again tomorrow, same time, and we see how can we conclude this, and we'll see the lessons learned from you if you've achieved something. Like we've been telling you all along, it is always good that the more you practice any programming language, the more it becomes clear. Don't worry about in case you get errors. Those errors have solutions. Everything has a solution. It's about, you know, being positive and check again with Google. Like we said, with our community, all those problems have been encountered and the problems are being solved. The other thing that you can do in order to avoid most of these particular errors is to always use an updated version, because as they update these versions, they work on the challenges that users always face as they journey with their program. Thank you so much. Kindly type if you're done with the survey. What about certificates? We'll see certificates tomorrow. The Secretariat will communicate more about it. Don't worry. Done, done. We need reply. Please don't go unless when you've okay, done with the survey. All right. Thank you so much and have a